Because we interchange the positions of x and y to find the inverse of a function, the point b comma a lies on the graph of the inverse anytime the point a comma b lies on the graph of the original function. So what that means is that if 3, 2 is on the original, then what will be on the inverse? 2, 3. Yeah, all it does is it switches them, switches the x's with the y's. Because of that, the graphs of inverses will always be, they say reflections, but another way of saying it is symmetric about the line y equals x. That's how you tell from a graph if two things are inverses. If they have symmetry along the line that runs through y equals x. 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, negative 1, negative 1. If you draw that line dotted and fold the graph along that line, the two sides would have to match up perfectly. So for this example, let's find the inverse of y equals x cubed plus 3. And then we're going to graph the function and its inverse on the same set of coordinate axes. So if we start with y equals x cubed plus 3, that's our original. And then I switch the x's with the y's. And I try to isolate y. That will be my inverse function. So if I subtract 3 from both sides, I have x minus 3 equals y cubed. And then how do I get rid of the cube?
Cube root.
Cube root both sides. We have cube root. And that gives us y equals the cube root of x minus 3. So this is our inverse. So the problem's half over. Now I want to graph them both. So we'll go kind of slow here. And I want to graph y equals x cubed plus 3. Now we know that's the parent function, y equals x cubed, just shifted up 3 units. We could either graph it that way, or we could just plug some x's in, which is what I think we should do. It's pretty easy. If I let x be 0, what's y? 3. If I let x be 1, what's y? 1 cubed is 1, 1 plus 3 is 4. How about 2? 2 cubed is 8, and 8 plus 3 is 11. So I'm here at 8, 9, 10, 11. So he's way up there. What about negative 1? If I let x be negative 1, negative 1 cubed is negative 1, plus 3 is 2. And then negative 2, if I put negative 2 in for x right here, negative 2 cubed is negative 8, plus 3 is negative 5. So negative 2, negative 1, 2, 3, 4, 5. Okay, there's the original function. It's just like the graph of y equals x cubed, but it has been moved up 3 spaces. Now let's try to graph the inverse. So I think I will use red for the inverse here. The inverse is a little trickier.
You can't just like remember the parent function and move it.
You could just do the parent function and move it to the right 3 spaces. Do y'all want to do that?
Yes.
Okay. So what are the points that go on the parent function y equals the cube root of x? We know they are 0, 0, 1, 1, right? Negative 1, negative 1. 8 comma what? 2. And negative 8 comma negative 2. Those are the points that we go on the parent function y equals cube root of x. This guy I want to graph is the exact same, but he's been moved every point to the right 3 units. So we could do that. So I start at 0, 0, but then I move it to the 1, 2, 3. 1, 1, 1, 2, 3. Negative 1, negative 1, 1, 2, 3. Positive 8, positive 2. Now he's going to be way over here off my graph, so I can't really see him very well. But negative 8, negative 2, and then move him to the right 3 units. So if we imagine drawing that, he looks kind of like this graph here. Do you guys see that? Okay. Take a look at the line that runs through y equals x. That's this line right here. Do you see how if I folded those guys, they would match up perfectly? That's what that means. If you graph inverses, you could always fold them along that diagonal line where y equals just x, where it goes through 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, and so on. Another way to look at it is this. What is this point right here? That's 3, 0, right? What's this point? 0, 3. See how they're the reverse of each other? The x equals the y? Yeah? That's true for every point on here if you check it. So that's how that's how a function is related to its inverse on a graph. So for our final example, we want to look at the function f of x equals x squared plus 3. Now that's a parabola. Do you guys understand that? Yeah? Okay. Let's look at it just real quick. It doesn't ask you to graph it, but I want you to look at it. That's the parabola that goes through here. And then if x is 1, it goes through 4. Negative 1 is 4. 2 is 7. And negative 2 is also 7. So there's the function y equals x squared plus 3. Do you notice that it's not 1 to 1? How do we know it's not 1 to 1? It doesn't pass the horizontal line test. Good. Okay, and so a lot of times we don't care. We can just still find the inverse of it. Do y'all understand that? So if we just found the inverse, we would say y equals x squared plus 3. Switch them out. X equals y squared plus 3. Subtract the 3. And then what? Take the... Now when you take the square root, what happens? You get a plus or minus square root of x minus 3. So the inverse of that function is equal to plus or minus square root of x minus 3. Are we all okay with that?
Yeah.
All right. Now, for some reason, and it's not particularly, it doesn't really matter so much for us, but for other times, like in applied math or applied science classes, you may only want to look at certain values of x. So you may want to make it 1 to 1. That's what they're telling you up here. And they say, we're going to restrict the domain so that x is only less than or equal to 0. Which basically means I'm going to take which half of this parabola off?
The right.
The right side, yeah. I'm going to leave that. I'm going to take this off right here. So if I let x be less than or equal to 0 only, it leaves me with just this half. Do you guys understand that? Okay. This guy right here, do you understand he is the sideways parabola? He's the positive square root and the negative square root that has been shifted to the right or left?
Right.
The right, yeah. So if we come over here, he's here, here, here. Let's see, 7. This is y equals positive square root of x minus 3. And I know I did that really, really fast, so it's okay. Don't freak out. And y equals negative square root of x minus 3. Which one of those should I keep if I want it to be the inverse of just this half? The top one or the bottom one? The bottom. I kept the negatives over here, so I want to keep the negatives over here as well, the negative y's. If you keep the negative x's, you want to keep the negative y's. So we're going to take off the top piece, even though it looks a little weird. And now you can see that these two guys are inverses of each other. Now they would have still been inverses of each other if we had left the whole graph. If we had left this and this, I just can't make it work. Not very pretty, but anyway. Do you see that they would still fold and match? Okay, but sometimes we want to restrict them. And if we take half of one, we take half of its inverse as well. That's what this slide is trying to get you to understand. So if I only keep the blue half here, which one of these would it be? Positive square root of x minus 3 or negative square root of x minus 3? If I only keep the blue half, is that the positive y's or the negative y's?
Negative.
Those are the negative y's. Okay, so that's what they're looking for in this case. Typically, if I ask you to do something like that, I just let you give me the whole inverse. I don't make you restrict it to the positives or the negatives or make it 1 to 1. But a lot of times, you know, we do want to throw out certain portions of the domain. Okay, I want to find the domain and range of just this piece right here. That's the last thing. What's the domain of the original? Negative infinity up to 0. I cut it off, less than or equal to 0. What's the range? From bottom to top, it starts at 3 and goes to infinity. Now watch this. Over here, what's the domain of the inverse? 3 to infinity. Oops. That's the domain of the inverse. What's the range of this inverse?
Negative infinity to
Negative infinity up to,
3.
not 3,
0.
the y value, 0. Negative infinity up to 0. Study those and tell me what you notice. This is the domain and range of the original. This is the domain and range of the inverse. What do you notice?
The domain of one is the range of
They are switched. The domain of one is the range of the other. Do y'all understand that? That is true every single time with inverses. So you know how up to now we've told you, oh, you have to graph it to find the range? The way to algebraically find the range is first find the inverse. And the domain of the inverse is the range of the function, of the original function. So that's the way algebraically to find the range. Takes a lot of time though, so most students would just rather look at the graph. But that is the way you can algebraically from here on out, if you want to find the range of something, what do?
find the inverse.
Find the inverse and you don't even have to graph the inverse. Find the inverse and find its restrictions and its domain. And the inverse's domain is the range of the original. So you might want to jot that down somewhere and put a big bubble around it.